Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industry and System Engineering. This lecture is multivariate time series analysis with a focus on a series of data examples using R. In this first example, I will illustrate the VAR model with a case study on predicting total moose population in Alaska. This case study was used to illustrate applicability of the ARIMA model in the previous lecture. In this lecture, we'll consider other factors which may impact the rise or fall of the moose population. The data provide irrelevant factors related to moose population, including population of Fairbanks, which is a city close to the location Unit 20A, from which we have the data on moose population, Alaska wolf population, average snowfall, and moose harvested. The years of the data are from 1965 to 2006, and the data are yearly. The data come from multiple sources, but are particularly acknowledged the Alaska Department of Fish and Game. The time series plot of the forecast of the factors in this dataset are here. We'll focus on the total moose population in this study. We can see that many of the factors provided have some overlapping patterns with this time series. The question we'll address in this lecture is whether we can forecast the total moose population with the aid of other factors. Does the wolf population impact the moose population? Does the moose population tend to decrease with heavy snow? Again, such questions can be addressed with a multivariate time series analysis. In a previous lecture, I developed forecast of the moose population based on two methods for modeling univariate time series: the ARIMA model and the model in which we first estimate a trend using non-parametric regression, then apply ARMA to the detrended time series. The forecasts are provided here, along with the observed data for comparison. The model in which we account for nonlinear trend, shown in blue, performs better than ARIMA, shown in red. As pointed out before, it is possible for other factors to impact the moose population. For example, the population of moose predators, wolves, for instance, can be a key indicator of the subsequent year's moose population. In general, a high predator population in a given year will not only influence the following year's moose population, but it also expected to have a more long-run effect. Additionally, natural factors such as weather and environmental conditions play an influential role. Average snow depth for a given year will be used as a measure of how harsh a particular winter season is. The population of the city of Fairbanks, the largest city in the region, as well as the number of moose harvested by hunters each year can reveal the effect of humans on the population of surrounding moose. Can we improve on the forecasting of Alaskan moose population by accounting for such factors? In summary, in this lesson, I briefly introduce the application in which we're interested in prediction of the Alaska moose population, and I will continue in the next lecture with the forecasting comparison between univariate time series models and the VAR model. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industry and System Engineering. This lecture is on multivariate time series analysis illustrated with data examples. On this lesson, I will illustrate the model fitting for the Alaska moose population. Because the objective of this analysis of the data on the total moose population in Alaska is to predict the moose population, we'll divide the data into training and testing, where the training data is used for fitting the model, and the testing data is used for evaluating the forecasting performance of the fitted models. Next, we only analyze the training data. In a previous lesson, we've learned that the data in the study are not stationary. Thus, we'll next assess whether differencing the time series will improve stationarity. Here we apply the first order difference first. Here are the time series plots for the first order difference. The first order difference time series for total moose population still has a seemingly increasing trend. For other time series, the first order is sufficient to make the difference time series approximately stationary. Considering higher order differences as provided on the slide, does remove the trend in the total moose population. However, we still identify some possible non-stationarity for the other factors. Also, it will make interpretation of the results and forecasting more challenging. We'll continue analyzing the first order difference data. We'll continue with applying the VAR modeling to the first order difference data. We first select the AR water using the VAR select R command using as input the multivariate time series and the maximum order allowed. Here it is equal to 20. The selected order for this particular data is 4. In order to fit a general unrestricted VAR model with no trend, we can use the VAR command specifying the selected order. Because we didn't specify any option for the type, the default is to fit only a constant for the mean with no trend. Furthermore, if we'd like to fit a restricted model obtained via some form of model selection, we can use the restrict command. In the next slides, I will present the model output for the total moose population from both models. This is the output for the total moose population from the unrestricted VAR model. The output provides the estimation of the coefficients along with statistical inference on the statistical significance of the coefficients. The order of the coefficient is as follows. The first 5 are for the lag 1 time series relationships for the 5 time series. The next 5 are for the lag 2, and so on. The last coefficient is for the constant or the mean of the time series. For example, the estimated coefficient for the relationship of lag t-1 of the total population in Fairbanks to the total moose population is 0.004. Since the p-value is large for this coefficient, we conclude that it's not statistically significant. The next coefficient is for the relationship with lag t-1 time series of the moose harvested, and its estimate is minus 1.41. Again, since the p-value is large, this coefficient is also not statistically significant. In fact, none of the coefficients is statistically significant since the p-values are all large. This lack of statistical significance is also reflected in the F-test for the auto-regression. For this test, the null hypothesis is that all coefficients are 0. Since the p-value is large, we conclude that it's plausible that all coefficients should be 0. Let's take a closer look at the restricted VAR. This is the output for the restricted VAR. The restricted VAR only includes the lag -1 time series for the total moose population, and the coefficient for this relationship is statistically significant. Moreover, by including this relationship alone, we explain 42% of the variability in the total moose population. Since none of the lag relationship with respect to other time series have been selected, we may conclude that other time series do not grandeur cause the total moose population. We'll test this formally. We apply here the Wald test, where the null hypothesis is that all coefficients corresponding to each of the 4 lagged time series, including total population in Fairbanks, moose harvested, average snow, and total wolf population, are 0, meaning that they do not grandeur cause the total moose population. The test is applied separately for each of the 4 time series. From this result, we find that there is no grandeur causality for Fairbanks population and wolf population, but there is a statistically significant grandeur causality with respect to the other 2 time series. The results from this grandeur causality analysis and the restrictive VAR model are not consistent. One reason for this inconsistency is that the model selection approach implemented in the R command var select decides on which variable to be included in a model based on the t-values rather than performing a more rigorous model selection approach. Thus, the hypothesis testing procedure provided on this slide will be more reliable in identifying grandeur causality. Since we found that there is grandeur causality with respect to only moose harvest and snow average, time series. Next, we'll explore a model with a reduced set of time series, including these two time series, and a time series corresponding to the change in the moose population. A similar analysis as before is performed. Based on this model, we now find that there is not a statistically significant grandeur causality for the change in the moose harvested onto the change of the total moose population, but there is a statistically significant grandeur causality for the change in average snow. Once more, comparing these results with those provided by the model, including all factors, we see again an inconsistency with respect to the grandeur causality for the change in moose harvested. While for the model including all factors there was a statistically significant grandeur causality, for the model with reduced number of factors is not. Thus, we conclude that there is a significant grandeur causality with respect to the average snow, but we do not have evidence for grandeur causality with respect to the other three factors. Last, we consider the model with the reduced number of time series to predict the total moose population for the last 4 observations of the time series. Here is the plot of the observed time series for the total moose population for the last 20 years of data, in black. We also compare the predictions based on the VAR model shown in green with the predictions derived in the previous lesson using the ARIMA model shown in blue, and the model in which the trend is fitted using a non-parametric model and the stationary process is fitted using ARMA. This prediction is shown in red. From this plot, the VAR model performs slightly better than the ARIMA model, although they both misfit the trend. The method in which the trend is fitted using the non-parametric regression performs significantly better, clearly capturing the decreasing trend, although it underpredicts for all 4 years. In summary, in this lesson, I illustrated model fit and comparison of univariate and multivariate time series models for the example we're interested to predict the total moose population. Thank you.